Welcome to this video on correlation, undoubtedly one of the more important topics in the entire CFA Level 1 curriculum, especially within quantitative methods. Now, the way I'm going to tackle correlation here goes above and beyond what you require, at least in this relevant learning module. The relevant learning module states interpret correlation between two variables, but later on within quantitative methods, and certainly later on within portfolio management, you still have to compute correlation. So I'm going to go above and beyond what's required. I'm going to compute correlation with you using the calculator, using the old hand method as well. If you like this video, do subscribe to the channel, consider joining as a member to get access to a wider range of videos as well. Anyway, let's get cracking. What I'm going to do is present you with some data, and I'm going to present that data on what we call a scatter plot. Now, a scatter plot is your standard sort of graph where you'll have two axes, and we'll use it to try and represent the relationship between two variables, which I'm unimaginatively going to just call X and Y. These could be the returns on two funds, a fund return, and some measure of economic conditions, etc. I'm not going to necessarily bother. Now, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. You get the idea. And on the y-axis, I'm going to have the same 1, 2, 3, 4, 5, 6, 7, 8. I don't think I need any more than this. And I'm just going to make up some numbers, right? So let's say that when x takes on a value of 2 is down here for x, y at the same time takes on a value of, sorry, I said 2, and I drew an arrow next to 3. Well, that's the combination. X takes on a value of 2, y takes on a value of 6. Let's also imagine that when x is 4, y is 4 as well. Okay, and let's have one more. When x takes on a value of 9, let's imagine that y takes on a value of 2. Okay, good. So we've got 3 points, a sample. I'm going to assume this is a sample of 3 data points, 3 observations. Good enough for me in terms of assessing what's going on here and computing correlation with you. Now, we'll try to gauge whether there's a relationship between these two. Now, there may be, and there appears to be something of more or less a linear relationship. When I say linear, I mean that we could attempt to try and fit a straight line that doesn't necessarily go through the points. They don't lie on the straight line, but they more or less do. So there seems to be a linear relationship, and the scatter plot allows us to gauge that. At the same time, it's easy to spot relationships on a scatter plot. They don't necessarily have to be linear. They could be non-linear, so there could be a curve that nicely fits in there, or you could just simply say, well, there isn't really much of a relationship because things are scattered all over the place. What a scatter plot also allows you to do, now this is something additional that your book talks about in terms of advantages of using scatter plots, is it allows you to assess visually whether there are some extreme values, so-called outliers, that may be ripe for trimming, for in some way excluding from your data set. So it doesn't necessarily, those outliers don't necessarily impact your data that much. Anyway, I'm going to focus on correlation, which will show us the strength of the linear relationship, if a linear relationship at all exists, which I think it does here. And we can see that its slope, the slope of the line, is negative. It's a downward sloping line, so the relationship seems to be inverse in the sense that when one variable has a high value, the other has a relatively small value, and vice versa. In order to calculate correlation, you need to start with covariance. So let me tell you how we do that. Sample covariance. This is And the reason why I say sample is that there are always, with these statistical measures of deviation or codependence, there's always a formula for sample and population versions of the same measure. Fortunately, nowadays in the exam, you just need to know the sample instead of the population and sample version. So we'll just focus on one. This is a measure of the extent to which two variables, our x and y, well, to the extent that they co-vary, meaning they move together. Okay, and the symbol, don't have to worry about, symbols. Nobody will ask you to write out a formula for sample covariance is S, and because we're measuring the covariance between these two, S between x and y. And this is the sort of full formula. We're going to take the sum, starting with I equal to 1 and finishing with n, of products as in the results of multiplication. And these products will be, let me write it out first and then apply it, and you'll see what we're doing here. Y bar divided by n minus 1. Okay, so in the top of the fraction, in the numerator, I've got two brackets which look very similar, except that one uses x's and one uses y's. xi is a specific value taken by x. For example, over here, x took on a value of 2. So 2 is one of the xi's. 4 is another value taken on by x. 9 is another value taken on by x. Okay, and the same thing goes for the y's. I've got the first y value was 6, then there was a 4, then there was a 2. And what we will in just a moment do is put in the actual values taken on by x and taken on by y at the same time, and calculate how those values deviate, how they are different, how much they are different, and in which direction. The sign will be important here, from the respective sample means, which we haven't computed yet. We'll calculate the means, the arithmetic means of the x and y values. And then we'll just divide by n minus 1, which is a way of averaging these products. You may be wondering, well, to calculate an average, you should probably ideally divide by n. Well, in statistics, you can do that, but when you're working with samples, you typically divide by n minus 1 to create what is known as an unbiased estimate or estimator of the population value, in this case the population covariance. You don't have to worry about this, but we divide by n minus 1. That's beyond the curriculum. So let me just write out these observations in sort of in tabular format, in table format. So I had 3 observations, 3 sets of values for x and for y. And previously I drew them, now I'm going to write them out. So the first combination of values was this one, this point on the scatter plot, a 2 for x and a 6 for y. So 2 and 6. Then we had 4 for both, a 4 and a 4. And the final combination was 9 taken on by x and 2 taken on by y. So a 9 and a 2. And because I'm going to need these, I will also compute the means. The mean value for x and the mean value for y very quickly. It shouldn't be too onerous, I don't think. So over here I've got 2 plus 4, that's 6. 6 plus 9 is 15. Well, 15 divided by 3, in this case I'm computing the simple arithmetic mean. So the mean value is 5. I'm not dividing by n minus 1, don't worry. And then here 6 plus 4, that's 10. 10 plus 2, that's 12. 12 divided by 3 is a nice round 4. Brilliant. So I've got my means. And now let me attempt to do the actual computation of covariance. So S, X, Y. Okay. So I'll take each value of x, I'll take each value of y, compute their product, well, not their product, deduct the mean value, and then, you know, add them all up. So let's start with the first combination. When x takes on a value of 2, and of course its mean, I'm deducting the x bar, which is the mean, I'm deducting the 5 over here, so this element. At the same time, y took on a value of 6. And the mean of y is 4. Okay. So, okay, that's where the 4 comes from. That's our first combination. What about the second one? When x is 4, y is 4 as well. So, once again, start with x, 4, deduct its mean value, which is that steady 5. You see that 5, which I'm deducting here, is going to stay constant throughout the example. And then for y, I take its value over here, 4, but I deduct this steady mean here. So the number I'm deducting stays the same. And then the final combination, which is, you know, I'm starting with the first combination and finishing with the third one, because my sample size, n, is equal to 3, simply. Then I'm going to have 9 from over here, of course, deduct that steady mean value for x, and naturally multiply by what y takes on 2 minus the mean for y4. Okay, good. As you can see, with with a sample of 3 observations, it's relatively simple. If you have more, you have to rely on a calculator, and anyway, I'll show you how to do this on the calculator in just a moment. And we still need to take the average, kind of average, by dividing the whole thing by n minus 1, which is simply 3 for n minus 1, so we'll be dividing by 2. Let's try to quickly do this on the calculator. Well, 2 minus 5 is of course 3 with a minus, multiplied by 6 minus 4, that's positive 2. Okay, so the first thing is minus 6. Then for the next one, I've got, I don't think I need a calculator for this right now, 4 minus 5, that's a negative 1, but multiplied by 0, so the second number is, the second product is 0. And then I've got 9 minus 5, which is 4, but 4 multiplied by minus 2, isn't it? So I've got a negative 8 here. So effectively, I have minus 6 plus 0 minus 8. That's negative 14 divided by 3 minus 1, that's 2, that's minus 7. And that's going to be my sample covariance. Now, there are 2 things I want you to appreciate about this. First of all, the sign of covariance is important, but the actual value, whether it's minus 7 or minus 70, is much less important, right? The sign is important. The actual value doesn't tell us much. Now, why is the sign important? Well, if, like in this case, the covariance is negative, what that implies is that when one variable, x, takes on values which are above the mean, then the other variable, y, takes on values which are below its respective mean. So this is just a tendency. Let's see if that's true. You see, when x took on a value of 2, which means below its mean, the mean for x was 5, the other variable, y, took on a value of 6, which was above its mean, and vice versa. When x was at 9, above its mean, y took on a value which was below its mean. As a result, the product of the product of these two deviations was negative, and we got an overall negative covariance. It doesn't always work, over here it's not perfect negative correlation. Over here we had covariance. Over here we had one of the x being below its mean, the other being exactly on the mean. So the general tendency is such. On the other hand, if Sxy, the covariance between the two, were to be 0, then we would say that x and y are unrelated. There isn't any sort of relationship between them, at least no linear relationship exists. It's all about linear relationships when you deal with covariance and correlation, which we'll get to next. And of course, if x and y, the covariance between them would come in as something positive, we would conclude that there is a positive relationship between them. Just like here, the tendency here is for an inverse or negative relationship. Hence, the line that I drew over here was downward sloping. Positive relationship probably exists. Linear relationship, meaning that when x is above its mean, then y has a tendency, to be also above its mean, and the other way around. When x is negative, the deviation from the mean is negative because x is below its mean, the y does the same. And then even if both are below their means, so each of these parentheses produces a negative difference, by multiplying them out, we get a positive result. Okay. Now, the problem with covariance is that it's not very useful, and you have to kind of appreciate this. Covariance is measured in units squared. So, for example, let's say these were fund returns, and this was 2%, 6%, and so on and so on. Effectively, this is also measured in percent. So you've got two worth of brackets, each one computing values in percentages, and because you're multiplying a percentage value by a percentage value, the result comes in at percentage squared, which is very difficult to interpret, impossible to interpret. And as I said, the actual value of covariance, whether it's -7 or -70 or -700, is meaningless. It really depends on the magnitude of the observations. Their size, it doesn't tell you anything meaningful or relative. Hence, we move on to something that is meaningful analytically, and that's correlation. The coefficient of correlation, which we'll come across later on in numerous points in this section of the curriculum, as well as in portfolio management. You'll come across this when you do linear regressions as well, and I'll explain it again using different numbers. Correlation is basically standardized covariance. And the formula for it, correlation, is denoted by R. Rxy, the correlation between the variables x and y, is Sxy, that's the covariance between them, divided by the product of Sx and Sy. These are basically our standard deviations for x and for y. Now, I want to compute this with you by hand before I move on to the calculator to show you how this can be done quickly. And anyway, remember, at this point in the curriculum, in this learning module, you're supposed to interpret correlation. But I think it's very important to know how to compute it anyway, or how it is computed, because that's the only way to really be able to interpret what it does and what it tells you. Right, so let's just quickly compute Sx, the standard deviation of x. It's very simple. You should remember this from previous videos when we were, I was talking about how you do standard deviation for a sample. So take the values for x, 2, 4, 9, and once again build brackets or parentheses. You take the actual value for x and you divide the mean from the sample for x. The mean was 5. So I take 2 and deduct 5. And I square this, remember? From previous videos you have to square. In a second bracket you're going to take the next value for x, which was a 4, and still deduct the same mean x bar, square it. And do the same for the third one. That was, let's see what the value was, 9. And we of course, well, let me try and fit this in over here so as not to extend my fraction too much. 9 minus the 5, okay, square that, managed to fit that in. And we divide by n minus 1, which is 3 minus 1. But if we left it like this, this would simply be variance. We have to take the square root to get to standard deviation. Of course, this is all covered in previous videos. So let's take my calculator. 2 minus 5 equals minus 3, square that. The next one is 4 minus 5 squared. Well, I know that's going to be 1. Of course, when you square, you get rid of the negative sign. And the final one is 4 squared. 9 minus 5 is 4, so we're actually getting plus 16 over here. Okay, so I've got 26. Deduct this by 3 minus 1, that's 2. And take this square root. Here we go. I'm going to try and be as precise as I can. 3.60555, 3 5s at the end. Well, I could be even more precise, but this is where I want to cut it off. Because the reason why I'm being so precise is that later I'll do this, in just a moment I'll do this on the calculator. I want you to see that we get the same result. What about the standard deviation for y? Well, once again I will construct a big fraction. I'm giving myself a little bit more space here and do the same thing here, but with the y values. We'll have 3 lots of these parentheses where we will stick in the actual values taken on by y and deduct their mean. So the first value was a 6, the mean is 4, the second value, okay, was a 4, and this third value was a 2. 4 minus 4 and 2 minus 4, and we divide by the same 3 minus 1, number of observations minus 1. So the first one is 2 squared, that's 4. The next one is 0, 4 minus 4, 0 squared. And the third one is minus 2 squared, so another 4. So I've got 8. 8 divided by 2, brilliant. Take the square root. That gives us 2.0. Excellent, nice and easy. So, lots of work, but we are finally able to compute correlation, Rxy. It's going to be covariance that I've got somewhere up here. Okay, covariance was minus 7. Divided by the product of these two standard deviations, so 3.60555 times 2. Let's see. 7 negative divided by, I opened a bracket, 3.60555 times 2 equals, okay, negative 0.9707. And that's correlation between these two. Now, I said correlation is standardized because it has specific properties. Before I go on to those, I just want to show you how to compute the same thing on the calculator, because you may need to do so in other places in the curriculum potentially, or you need to be able to work the relevant worksheet. Go to the data worksheet, which is hiding behind the key the digit 7. 7 has the secondary function data, so I press second 7, and over here you can input actual values for x and for y. So let's go back to my table. My first x is 2, so I'm simply doing 2, enter, hitting the down arrow, and I'm supposed to give the calculator the first value for y, which was this 6, enter, hit the down arrow again, input the second x value 4 and the corresponding y value 4 as well, and then the set of x and y's in the third observation, which was 9, enter, and 2, enter. And you can scroll up and down to see if you've got all your inputs correct. You can overwrite something, but I'm going straight to the menu next door, which is the stat menu. It's hiding behind the digit 8 as the secondary function of 8. So second 8, this gives me the stat worksheet, or the stat module, whatever it's called. Now press the down arrow. You can see n is 3, meaning that in the worksheet next door in the data, the calculator has recorded 3 sets of observations, and it's telling you, well, my computed x bar, the mean for x was 5. We know it was 5. Good. Now Sx, which was our computed standard deviation for x, it says 3.60555. Well, that's exactly what we computed. So as you can see, your calculator does this much more quickly. And it also does the population standard deviation computation, which basically differs from the other one because it divides not by n-1, but n. It's a number divided by 3 instead of 2. For y, the mean is 4. Well, we had a mean of 4 as well, I can tell from what we've got over here. Same standard deviation too, okay. Population standard deviation as well. Now, this will come in handy when you do regressions. This is the so-called intercept. So on if you were to plot a straight line, it would probably intercept the y-axis at a point of 6.69. Well, pretty close to the line I drew here, and it would have a slope, a negative slope of 0.53 minus 0.538. That's what you do when you get to linear regression. But very importantly for us, r, the correlation coefficient, it's minus 0.9707, which is exactly what we computed by hand on the calculator and using, old school pen and paper. Even if it's digital, it was still pen and paper, but you can see the result agrees. So I've confirmed, I guess, that the computation which we did was right. Brilliant, happy with that. Let's now talk about correlation and its properties. The properties of correlation. First of all, it's a standardized measure. I said it's standardized kind of covariance, and it's standardized in the sense that it can only range within a specific, it has upper and lower limits. The minimum value for correlation is going to be negative. So correlation has to be equal to or higher than -1 and less than or equal to +1. It cannot be higher or lower than those two. If you compute a correlation that is 0 or very close to 0, what that suggests is that there is no linear relationship between the two variables x and y. There may be another, relationship, one that would be depicted by some kind of curve function, but not a linear one. If you've got correlation that's negative, like we've got over here, minus 0.97, that suggests a negative linear relationship. Once again, between x and y. And the closer we get to -1, the more perfect that linear relationship is. -1 doesn't mean that the slope of the line is -1. No, we saw on the calculator there was something like -0.53. As the closer you get to -1, the more these points lie and snap to that straight line. If they were perfectly on a line, irrespective of its slope, you know, how steep that slope is or how flat that slope is, the more you get to, as long as the slope is negative, the more you get to -1 correlation. So this is something called perfect negative correlation. Okay, same thing with correlation above 0. That suggests a positive, but once again, linear relationship, and +1 means it's perfect positive. But once again, appreciate, it doesn't mean a slope of +1, as in if we increase x by 1 unit, y increases by 1 unit as well. No, it doesn't mean that. It's just that the points lie on a straight line perfectly, irrespective of the slope of the line itself. Okay, when I'm showing this, I think because my camera reverses the image, you probably see this the other way around. I'm not sure now what to do with that, but I'm very bad with orientation and trying to reverse things in my head, so don't just think about positive lines, positively sloped and negatively sloped lines. Okay, so let me just write that down. Correlation is not the same as the slope of the straight line. It's just about how closely the observations fit to a straight line. If it's 0, then they're all over the place. We're not able to really fit a line that tries to even vaguely connect them. And very importantly, correlation has no units of measurement. It's just a pure number. Look, if I told you before that covariance is measured in units squared, for example, in percentages squared, if these were fund returns, then standard deviation is measured in units, in the same units for which we've got the observations. So over here you would have percent times percent, so once again percent squared, and the percent and the sign and the and the units cancel out. What's also very important is that the sign for correlation, whether it's negative or positive, depends simply on covariance, because standard deviations always come in as positive numbers, because here you're squaring. So if you've got negative covariance, you're going to have negative correlation. If you've got positive correlation, you must have positive covariance, right? That's something also to keep in mind and potentially remember in case of theoretical questions in the exam. Now, very importantly, you should be aware of some of the limitations of using correlation in analysis. Something I've mentioned already, it does not capture non-linear relationships. So if you have a scatter plot and your data seems to be forming a bit of a smile, well, you can't draw a straight line through a smile. Correlation will come in more or less close to 0 or something like that. But you could draw a curve through these, which could be described with a function. It's just not a linear one. So correlation wouldn't be able to capture this. The second thing is it may be unreliable in the presence of outliers. If you've got outliers in your data set, correlation may go wrong. So you may want to exclude outliers and focus on what's sort of within the core of the data. And just because there seems to be some kind of dependency, it doesn't mean that there is an actual there is causation. So correlation does not imply causation. It doesn't mean that one thing drives the other, right? Just because they co-vary quite well. And there is an important term that you need to know: spurious correlation, which can mean a couple of things, but it's sort of false analysis of false conclusions drawn from correlation. Correlation may come in at quite a high or low number, in the sense of being close to +1 or close to -1. You may think, oh yes, there is a relationship, but it may just be a chance relationship. Yeah. And what often happens as well is that correlation may not arise from a direct relationship between X and Y, but their relationship to some third variable. And the curriculum gives a really nice example, which I find appealing because it's so nice and simple. There is probably a strong correlation between somebody's height, how tall they are, and the extent of their vocabulary. What range of words they've mastered. And you could say, well, yeah, okay, probably height and vocab are positively correlated, brilliant, so one drives the other. No, and nor is it the other way around. There is no link. Well, there is a link, but you can't say that one causes the other. It's to do with something else. Height is absolutely positively related to age. So age drives height. As this, the younger we are, the smaller we are typically. Obviously, that stops at some point. And age also drives the extent of our vocab. And that's where the relationship is, not between X and Y. There's something else, we could call it Z, that the two variables are actually positively related to.